This is the last lecture from Chapter 7, and it's a review of stoichiometry, but it's stoichiometry for chemical reactions carried out in solution. So we're going to be dealing a lot with the molarity formula and how to do stoichiometry using that. Alrighty, so looking at the top half of this chart is our regular stoichiometry map. We're used to going from grams of, let's say, some reactant to moles of that reactant, and then using mole ratio in the balanced chemical equation to get moles of, let's say, for usually one of the products, etc. And what we're going to be focusing on more often than not when we're talking about chemical reactions are solutions, things dissolved in other things. And so rather than grams, it's more common for us to get a value in terms of molarity or liters of solution. And so the bottom half is what we're going to be looking at in this PowerPoint. So just to kind of review the formulas we're going through, the primary one is molarity, moles of solute. Okay, so this is how you're going to get to moles of one of the reactants. Over liters of the entire solution. And so if you're one of the algebra challenged, the little magic triangle can help you be able to rearrange the molarity equation to solve for either liters, which if you cover up whatever you're solving for, you should cover up, right? So if you're solving for liters, that tells you it's going to be moles over molarity. And similarly, if you're solving for moles, that tells you that it is going to be moles times liter. Excuse me, molarity times liter. So be real familiar with rearranging the molarity equation to solve for any of those three variables. So again, we're going to be focusing on the bottom half of that stoichiometry map. So very often you will be given, let's say, the volume, 25 milliliters of sodium hydroxide or something. And it'll ask you, okay, how much sodium chloride are you going to make in that reaction? So what you're going to have to do, if you're given volume of something, you're going to have to convert that to moles, and you do that by using the molarity equation. If you rearrange the molarity equation and you're trying to get to moles, this is probably the most common calculation you're going to do in solution stoichiometry, is molarity times liter gives you mole. So this one you definitely want to have at the edge of your brain at all time, okay? Molarity times liter equals moles. Okay, and then the rest of the stoichiometry is what you're used to. Use the mole ratio from the balanced chemical reaction to get from moles of any one substance in the reaction to moles of any other substance in the reaction. So let's look at an example, just regular stoichiometry. Okay, so we have a combustion reaction here. And if you're not already real comfortable with combustion reactions, now's the time to make sure you are. Because I might say to you, I might tell you that this is octane, and then say, write out a balanced combustion reaction of octane and do some stoichiometry on it. So you would need to be able to write the rest of this combustion reaction. So you need to remember that in a combustion reaction, one of the reactants is always molecular oxygen, and that the products, at least in a complete combustion, are always carbon dioxide and water. And then, of course, you would just need to balance the reaction. But in any case, back to our stoichiometry. Our given information, which is what you always want to start with, is 10 kilograms of octane. So the first thing I would want to do is get out of kilograms. I know that I'm going to need grams, okay? So let's use dimensional analysis to show our work, make sure we keep units straight. And I know that there are 1,000 grams in 1 kilogram. All right, so that tells me that I have 10,000 grams of the octane to begin with. Now, with any stoichiometry problem, if you're given information is for one substance, in this case octane, and it's asking you for quantity of a different substance, whether it's the other reactant or one of the products, you will have to get to moles. So even if you don't know what you're doing in a stoichiometry problem, if you can work your way to moles, you're usually halfway there. So right off the bat, even if I wasn't quite sure what I was doing, I would convert the grams that I have of octane into moles, okay? And so anytime you're converting between grams and moles, moles to grams, you need the molar mass. So real quickly, look up the molar mass of octane. I'm going to do it off to the side here because I'm being lazy. So we have, let's see, carbons, 12.01 grams per mole. We have 8 carbons, 96.08. We have 18 hydrogens. And so the molar mass of octane, 114.26. Alrighty, so I'm going to go ahead and go to the next page because I think I have it all neatly worked out for you there. Yes, I do. So I'm going to cross out the things I can, the units that are the same on the diagonal. If you were asked to show your work, this is how you would do it. Some students prefer to do one calculation at a time and get intermediate answers. That's perfectly fine too. All right, let's see. So now grams of octane cancels, moles of octane cancels, and moles of CO2 cancel. Okay, so what did we do here? We went from grams of one substance to moles of that substance. Then we used mole ratio right here to go to moles of the substance the question is asking for, which is CO2. And then since the question wants mass or grams of CO2, our last step is going to be going from moles of CO2 to grams. So if this stoichiometry map helps you, you may want to jot it down or print it out. All right, here's one for you to practice. So I would recommend turning off the video. You can go back to the stoichiometry map if you need it and see how you can do this problem, and then I'll work it out for you on the next page. All right, the first challenge you have in this reaction is that rather than given formulas or a balanced reaction, you are given the word names. And so this is worth reminding you at this point that barium hydroxide, that is an ionic compound, it also happens to be a base. But remember, to come up with the correct ionic formula, you want to first, it's a two-step process, you want to first assign charges of the two ions. Barium's in group 2A, so it has a charge of 2A. Hydroxide is a polyatomic. Hopefully you have its charge memorized by now, which is -1. So if we crisscross the charges, we end up with the correct formula for barium hydroxide. And hydrochloric acid is pretty easy. I think most of us know that. We need it, again, barium chloride. So when an acid and a base, a strong acid and a strong base react, what are the products? They are always a salt, which is the nickname for an ionic compound, and water. So now let's go back to getting the right formula for barium chloride. When you crisscross the charges, you get BaCl2 plus H2O. Now we simply need to worry about balancing the reactions. So I see that I need a 2 in front of hydrochloric acid and a 2 in front of water. And there I go. So here is my balanced reaction, and now I'm going to start doing stoichiometry. The problem tells us that our hydrochloric acid solution is 0.15 molar and that we use 150 milliliters of it in this reaction. And the problem wants to know the grams of barium hydroxide that's needed to react entirely with this acid. So I mentioned a few slides ago, I'm not sure if you remembered, that when you are doing stoichiometry in solution, quite often the first step is going to be multiplying volume by molarity to get moles of the given substance. So I'm going to write the formula real quick here. Molarity equals moles per liter. So remember, if you're trying to get mole and you rearrange this, mole equals molarity times liters. So that's how I'm going to start. 0.15, and I'm going to write molarity as moles per liter because it lets me follow my units a little bit better. And I need liters from milliliters. So let's do a quick calculation of that. There are 1,000 milliliters in 1 liter. So I really have 0.150 liter of HCl. That has to go on top, so the liters cancel. And that then tells me that the moles of HCl that I have are 0.0225. Now I'm not going to round it yet, even though I know I have too many sig figs. I'm going to wait till I'm all done. And I'm going to keep up with what substance I'm using so that I can keep straight where I am better. All right, so now I know the moles that I have of HCl, and I'm trying to get to how much barium hydroxide I need. So anytime you're going from one substance to a different substance in the reaction, you need to use mole ratio from the balanced chemical reaction to do so. It's got to be mole to mole comparison. All right, so I can see from the coefficients that I have 2 moles of HCl for every 1 mole of barium hydroxide that's needed. And so that tells me that the moles of barium hydroxide I need, and again, I'm not rounding yet. All right, so you can do this in one continuous long dimensional analysis problem like I did on the last page, or you can do it stepwise, kind of like I'm doing it now, whatever is easier for you. All right, so the problem asked me for grams of barium hydroxide though, so now I need to do one more step and I need to convert that barium hydroxide to moles. In order to cancel the moles, I know I need moles in the bottom. I'm trying to get to grams, so I'm going to put that on the top. And anytime you're converting between moles and grams or grams and moles, you need the molar mass. And the molar mass of barium hydroxide is 171.34 grams per mole. And so now the mass that I have of barium, or that's required to react with all the given HCl, is 1.9. How many sig figs should I use? Well, if I did this right, this has 2 sig figs, and that has 3. So that, I can't remember if this is 0 knot or not. But either way, 2 or 3 sig figs. We'll just do that to be safe. All right, barium hydroxide. And that's the answer, okay? So there are about a zillion different ways to word these stoichiometry problems in solution, so I suggest doing as many as you can to practice. Sometimes the stoichiometry problems will be given in terms of a titration. So review, in case you're not real familiar with titrations, is you typically have an unknown compound. And by unknown, I don't mean, you do know the identity. Like, let's say it's calcium carbonate. So you know what the general makeup, you just don't know the concentration. So typically the Erlenmeyer flask underneath the burette has an unknown concentration of something. And what you're going to do to figure out that concentration is you're going to fill the burette with something that reacts with the unknown. And you obviously also know very precisely the concentration of what you're titrating with. And so through some stoichiometry, you can then figure out the concentration of the unknown substance. And so, for example, problem might say Let's see, might say something like, I need a different color, don't I? So let's say it takes 37 milliliters of, let's imagine the HCl is in the burette. And we've got to say concentration. So let's just say it's 1.0 molar HCl. It takes 37 mils of it to completely react with the unknown concentration of the substance in the flask. So let's just say that's NaOH. And let's say that we have 50 mils of NaOH in the Erlenmeyer flask. So then it might say, okay, what is the molarity of, or the concentration of the unknown? In this case, I called some type of, or some concentration of NaOH. All right, so that's another typical format. So just make sure you practice some of these. All right, so this is very similar to the titration example that I just discussed. So let's walk through and see if we can figure this out. Acid-base titrations are very common because acids and bases react very nicely with each other, especially if they're strong acids and bases. It pushes it essentially 100% to completion. All right, so again, remember what an acid-base reaction forms in case you are not given the reaction. An acid and base will react, at least a strong acid and base, will react to give you a salt, ionic compound, and water. Okay, and so now what this is telling us is the sulfuric acid, I'm going to put it above it. We have 25 milliliters of the sulfuric acid, and it is 0.25 molar. And we know the molarity of, no, we want to know the molarity of the sodium hydroxide, but we know that we used 23.4 mils. Right. So I need a lighter pen. Let's try green. Okay. So just to kind of remind you of where we're going from, you have information about both reactants. You have some information about sodium hydroxide, and you have more information about sulfuric acid. You're always going to start with the substance that you have the most information on, okay? We know the volume and we know the molarity of sulfuric acid. Do you remember me saying that most often in solution stoichiometry, you're going to be multiplying molarity times liters to get moles? Well, that's exactly what we're going to do here, right? So we have 25 milliliters, which is 0.025 liters. And we're going to multiply that by the molarity of the same solution, which is 0.25 moles per liter. And the liters will cancel. And so when we multiply those two together, we get 0.00625 moles of H2SO4. All right, so this is what we did so far. We multiplied molarity times volume. We got moles of H2SO4. It's good to have a plan. We need to get to moles of the substance they're asking about, which is NaOH. And so, as always, we're going to use mole ratio from the balanced reaction as a conversion factor. So I'm going to move this down here. 0.00625 moles of H2SO4. Be very careful in your mole ratio to look at the balanced reaction. So looking at the balanced reaction, I see that I have 1 mole of H2SO4 that reacts for every 2 NaOH that react. So the moles I'm going to use up or need in this reaction is going to be 0.0, 10, one more, 5. there, I hope. So that is moles of NaOH. Now the problem is we're at NaOH, which is great. The problem is asking us now for molarity of NaOH, and all we have so far are moles. So now ask yourself, how do you get from moles to molarity? Okay, so molarity is moles over liter. So if I have moles, I just need to divide it by liters. So if we go down here and I take 0.0125 moles, divide it by how many liters I have of NaOH, and go back to the problem, 23.4. So I need to convert that to liters, so I'm going to divide the moles by 0.0234 liters. And I'm going to go ahead and see what that gives me. 0.0125 divided by 0.0234. So that tells me that the molarity that I need of NaOH to react with this quantity of H2SO4 is 0.534 molarity. That should be the answer. And we lucked out. That is actually the answer. Another sample problem, even if the problem doesn't talk about a chemical reaction, but it asks about some interaction between one substance and another, you still need to use stoichiometry, okay? So let's walk through this. Copper sulfate, this is clearly an ionic compound since it has a metal. So copper is Cu, sulfate is a polyatomic. You should know that because it ends in ate or ite. So we're going to look that up if you don't remember. It's SO4 with a -2 charge. Copper, we know it's +2 because of the Roman numeral. Remember, that's how transition metals are named. A Roman numeral tells us the charge of the transition metal. All right, so then if we combine these in a 1-to-1 so that we get a neutral ionic compound, it's simply KuSO4. And so this problem is telling you that it is going to react with zinc. And you may not have learned single replacement, so if not, this is not a concern. And you'll see in a minute that we do not even need to know the products to solve this problem. But I'm just going to show you in a single replacement, two metal ions switch places. So you end up with zinc, sulfate, and copper metal. Alrighty, but in any case, it's all a 1-to-1. And so that's all we need for this problem. I like to write the quantities that the problem gives me below the substance. So I know that I have 1 gram of zinc, and the problem also told me that I have 0.1 molar solution of copper sulfate. And since the first step in pretty much any stoichiometry reaction is to find moles of something, I know that I can't get to moles of copper sulfate just from molarity. I would need volume also. So I'm going to have to start with zinc. 1 gram of zinc, again, anytime you're converting between grams and moles, that means you need the molar mass of the substance. The molar mass of zinc is 65.38 grams per mole. So I'm going to go ahead and cancel the grams. Good. So now I'm at moles of one of the substances. Remember, once you reach moles, then you want to use mole ratio to get from the moles that you already have to moles of what the problem is asking for. Problem's asking for copper sulfate. So I'm trying to go to zinc to moles of copper sulfate. So I'm going to go to the balanced reaction. It's all 1-to-1. And so it's not really going to change anything, isn't it? So let's see now. If I take 1 divided by 65.38, the mole ratio is the same. I am going to get 0.015 I'm going to carry a couple of extra sig figs just until I'm done. And at this point, I'm going to have moles of copper sulfate. All right, so I'm at copper sulfate, which is what the problem wants, but what do they want to know? They want to know what volume of copper sulfate, and I have moles. Okay, so we know that moles and volume are related by the formula molarity. So just to put it up here again in two different ways. If I am trying to find volume, liters, okay, I would need to rearrange this equation, right? I don't know why that happened. There we go. To solve for liters. So if I rearrange the molarity equation, I know that it would be liters equals moles divided by molarity. If you would rather use this magic triangle, whatever you're trying to solve for, you're going to cover up, and then what's left is what you're going to do. So this tells you that moles divided by molarity, same thing. All right, so let's go ahead and do it. So the liters of copper sulfate needed is going to equal the moles that we just found of copper sulfate divided by the molarity of the copper sulfate, which was given moles per liter. All right, so what's going to happen is the moles in the numerator and denominator are going to cancel. And so that tells you that liters of copper sulfate, 0.52 liters. That's not very much. Alrighty, so that's it for that problem. One last question in this PowerPoint. I like questions that tie in some information from what we've just learned, as well as information that we've learned from past units. It helps you kind of keep things fresh. So let's say what they're asking here. It's asking for molarity, okay, moles per liter, and also pH, okay. So just to remind you, the formula for pH is minus log of hydronium ion concentration. And what do we know here? We're going to dissolve 1.5 grams of HCl in 1 liter of solution. Okay, it's an aqueous solution. All right, so what are the molarity? What's the molarity of that? All right, so what is molarity? It's moles per liter. Okay, I have liters. It's 1. I need to find moles. I know that I can find moles from grams, so let's do that. 1.5 grams of HCl. Again, anytime you're going from grams to moles or moles to gram, you need the molar mass of the substance. The molar mass of HCl, I believe, is 36.5 grams per mole. And doing that calculation, oops, let me start over. Tells me that I have 0.041 moles of HCl. So now to get molarity, I'm just going to divide by liters. I only have 1 liter. That's not going to change anything. So then my molarity is 0.041 molarity of HCl. All right, let's see if you remember anything about pH. So pH minus log concentration of hydronium ion. All right, I know what the concentration of HCl is. I just found it, right? 0.041 molar. So how do I find the concentration of hydronium ion from the concentration of HCl? Well, I'm going to remind you that strong acids, and HCl is a strong acid, dissociate 100% in water to form the ion. So HCl, the instant you put it in water, 100% of it is going to dissociate to give us hydronium ion and the chloride anion. none of this original intact HCl will be left. And so whatever the original concentration of HCl was, in this case 0.041, that is the exact concentration of hydronium ion we're going to end up with in water. So then to get pH, all we're going to do is take minus log of, whoopsie, I don't know how I did that. Minus log of 0.041. That will give us the pH. So let me do that. That gives us a pH of 1.39. Always ask yourself when you're calculating pH if that makes sense, okay? 1.39 is quite acidic. Does it make sense that you would have an acidic solution? Why, yes, as a matter of fact, it does, because we are working with HCl, which is a pretty strong acid. That is it for solution stoichiometry.